So this is CS 109 Lab 4, and today we're going to talk about regression, as well as some sort of resampling tools. We're going to talk about mostly linear regression, but I am going to cover logistic regression at the end. For your next homework, you're going to actually do linear regression a lot, so it's good to learn all the tools and the plotting techniques for linear regression. So actually, one of my favorite things. So this is XKCD, obviously. It's a plot about linear, just talking about regression in general and extrapolation. So we're going to talk about that a bit. And there are obviously boundaries for extrapolation. And it's generally within your data set. Can you extrapolate, or within the range of your data, can you extrapolate? Not just everywhere and anywhere. Okay, so first, so most of you have taken basic statistics and probability, but I'm just going to do a quick overview of linear regression. So there's several reasons to do linear regression. The main reason that we're going to talk about is to build a predictive model, as well as sort of understanding the strength of relationships between variables. So for a predictive model, you have some outcome y. So I'll call it outcome. Some people call it target or something like that. And then you have some features that you would hope can predict this outcome. So that's one way that we'll use a linear regression. The other way is to model the strength of the relationship. So you can look at an outcome and see how sort of influential a particular variable is, or relative to other variables, how influential a particular variable is. So this is just a quick overview of linear regression. So there's a Wikipedia article here linked. So if you don't remember or just want to brush up even more, please read that. It's very detailed, maybe overly detailed, but it's all there. The way that it works is that you assume that there's a linear relationship between your explanatory variables and your outcome, so your x and your y, and you believe that your outcome is somehow related to x this way. And you can also do multiple linear regression, which we'll talk about a bit later. And in that case, the linear relationship holds for all x's, and the relationship strength is kind of in here. So if beta is very big relative to the other ones, it influences y a bit more than the others. So we're going to talk about the assumptions that go into linear regression. But the way that it works, and this is important for interpretation, is that if you look at any particular value of x, the distribution of the y's is going to be assumed to be normal. And not only that, but for different values of y, the spread of the normals are about the same. So that's called homoscedasticity. The spread is the same, and then the other one is just the assumption of linear regression, because we have to assume something in order to be able to analyze this. So that is one of the big assumptions. We'll see an example data set where linear regression does a good job at fitting, but it actually fails assumption. So we just have to be careful about things like that, because we could always do linear regression, but it's not always a good idea. Okay, so and then this next part, I'm just going to talk about sort of overview two separate ways in which we can actually find these betas, find the strength of relationships between the predictors and the outcome. So one of the ways is it's called least squares, and the way it works is essentially this is just the loss function, and it's a function of two variables here. So we're going to try to find the two variables that minimize this quantity, to minimize the sum of squared errors, and so it's just an optimization problem from this perspective. But another way to do it is actually that the betas solve this weird linear system. If you just this is a vector, this is a matrix, that's a vector. If this doesn't make any sense, just forget it, because we're never actually going to do it. But just so you know, to solve this thing here, we actually need x transpose x to be invertible. And if you remember linear algebra theory, what that says is that, or what that means is that these things have to be, all the columns have to be linearly independent. And what that means is that you can't have features that are too similar to each other. So if you have features that are exact same, that means you're rank deficient and things will explode. It'll be like non-singular. But if you get that error, that's what happened. And you will get that error sometimes. Okay, so that's sort of the brief overview. Oh, also this hat thing here. It's like, I don't know where statisticians came up with it. So statisticians came up with the hat, and I have no idea why, but if whenever you hear statisticians talking or people who work in statistics say something hat, it means that's an estimate of the thing that they hatted. Statisticians. So for this, we're going to look at a quick example. So there's a data set called the Boston Housing Data Set, and it shows up in a ton of different machine learning applications. It's actually, so if you go to this link here, it's actually UC Irvine. Oh, wait. Oh, no, this is scikit-learn. Oh, it's actually also on the UC Irvine machine learning database. Yeah, this is, oh, wait, no. Oh, I clicked on the wrong one, that's why. Okay. There it is. That makes more sense. So UC Irvine has this gigantic machine learning repository. CMU has something similar, but it's just basically a ton of data sets that serve specific purposes. This one we can use for linear regression because all the things that you want to predict, like the median house price for a particular region or for a particular part of the city. So we're going to use this data set. So you can load it from scikit-learn as well as go grab it from UC Irvine. But it's just here for us at our fingertips, so it's no big deal. So there are here 506 rows and 13 columns, and the 13 columns are going to be the features. And so actually, let's have a look at this. So they actually built in a thing that has the description of all the features. There are 13 total features: the per capita crime rate in each town, the proportion of residential land zone, blah blah blah. So all this is like information about each particular region, each particular town, and the outcome that we're interested in is the median house price. So the first thing we're going to do, oops, I forgot to load. Don't forget to load this. sklearn worked. Okay. Okay, so this is the actual data, and you see that they're all numeric, which is great because linear regression, you can do linear regression on like 0, 1 variables as well, but it's actually meant for continuous features. So here's just a sort of just a list of them, but you notice that they don't actually have names, which is kind of annoying. So let's actually append the names to it, just so that when we see it, we know what this is. So this is the crime rate per capita. This is, I think, the median or the average age. The proportion of owner-occupied units. So it's in 100 there. Okay, so here's the features. And so they actually, the way that they structured this is kind of strange because they wanted you to do linear regression. So they had all the features in one thing, and then the outcome that we're interested in, meaning the price of the median house in that town, they had it separately because in some packages you give it to them separately and then it figures it out. But for us, we're actually just going to append it there. So you can see, so this is the head of the new appended data frame. Okay, so you can do just a quick describe. It's always really a good idea to try to get an idea for what the data looks like. So it's nice to see that there's 506 across. You can see the averages, the standard deviations. So just to get a rough idea of what these numbers look like. So here, this is nice because you know that if it goes up to 100, Zn, I forgot what that was, but you know that it only caps up to 100, and this caps up to 1. So this is probably a fraction. This is probably a percent, things like that. So it's really good to just get an idea of your data, especially if you actually collected it like you did in homework 1, because there are obviously a ton of things that can go wrong. This is a very nice clean data set though, so it's not a big deal. Okay, so the next thing I want to do is just sort of explore the data a bit. And so this is just a scatter plot of the per capita crime rate for each town, and then compared to the housing prices. So you see there's some interesting things going on. Obviously, the per capita crime rate can't be less than 0, so it kind of gets squished down this way. Not only that, but it seems that if we were to project everything down, make a little histogram here, you can see that most of them, I mean, that's great, but yeah, most of the per capita crime rate is very low. And there also seems to be a ceiling here. So there's nothing above 50, which is interesting, and that's something we wouldn't have noticed if we hadn't looked at this. And then we can do the same thing for other variables. So this one's a little bit more interesting. It kind of already, so if you've seen linear regressions before, this is kind of ripe for linear regression fitting. It's sort of football shaped is what they say in stats books, but you don't need to say that. It's kind of oblong here, and it has a linear trend going upward. But it does have the ceiling here, which is interesting. We should probably look into that. It's probably somewhere in the documentation. I haven't looked at it, but okay. So because I said it was kind of ripe for linear regression, what I did was actually this is in a different. This is in the Seaborn module. There's a function called redsplot, and it actually does the same thing as before. It plots the scatter, but it also fits a line, and so. You can't really see it too well here, but on your computer you should be able to see a bit of a, yeah, it's kind of there, but it's faded. Anyway, a bit of a it's called a confidence band. So that gives you sort of a rough idea of where the average is for any particular value of RM, which is the, what was RM again? Number of rooms per dwelling. So this makes a lot of sense that this is so linear. Bigger houses, more expensive. So another thing we can look at, just sort of to get a even better idea of the prices, is this pupil to teacher ratio in the town. So this is kind of interesting. You can definitely see that there is some trend going on. It might actually be like this is very, very wide ranging, meaning what is this, 13. Has a wide range here, whilst these like maybe 19 are a bit tighter. But you notice that they're also in bands, which makes a lot of sense. Well, does it? I don't know. But anyway, so it's really good to explore your data. And I'm just going to give you guys code to make some histograms. We talked about the crime rate per capita, and here's the histogram for it. So there's a lot of towns that have under 10. And so here's another one. This is just the actual housing prices, and you can see the sharp cutoff there. Probably there was another mound, but I'll have to look into that. Okay, so how do we do linear regression on this? So we can use scikit-learn has a linear regression model. Linear regression function. And so we can do that here. So we can actually insert options into here. So we'll see that in a bit. But the default options are, so the fit intercept is true, meaning that back in our equation, there is going to be a beta 0, and sometimes you don't want that. You want it to fit through 0, in which case you should add fit intercept equals false here. And then in here, it's not going to normalize. We won't talk about normalization today, but we will eventually, because it does become important with sort of more complex regression techniques and prediction techniques. Okay, so you can actually see some of the things that are inside this this module, I guess, so you can fit the linear regression. You can use predict and score, which returns the R square, and that'll become important when you're actually assessing the model fit, things like that. So let's actually fit the model. So that's here. If we look at the intercept coefficient, so the intercept coefficient is about 36. That means that basically the average y is going to be the average price is going to be about 36. And then we can see that we won't actually print out 13 coefficients because there are a lot of them, and they're not actually that meaningful to us right now. Well, actually, no, we will. Okay, so here they are. So here are the different estimated coefficients. They don't have, I didn't print out the standard errors, but that'll be important to look at later on. But we'll talk about interpreting these in a bit. What I want to talk about now is looking at the predicted prices. So if we look at the first 5 counties, here are the predicted median the predicted median house prices for each of the first 5 towns. But actually, so here's the histogram of the predicted values, and you see that it actually missed that feature that we were talking about earlier, and it's perfectly, it's much more symmetric. It doesn't have any extra stuff, and this is because that assumption starts playing a role here. The assumption that we have normal residuals, it does start showing up, and so and it actually shows up here as well. If we plot the actual prices against the predicted prices, we see that there is a cutoff in the actual prices, whilst there's not really a cutoff here because you assume that it's going to keep going, and so you start seeing things like that here, and so it's kind of interesting just to have a look at these when you're doing actually a regression. Yeah, and so one thing that's kind of I'm not sure if it's just my eye or not, but you guys can tell me or think about it, is that this isn't a perfectly linear line, right? There's some curvature here, and what does that mean? So so it sort of means that for higher prices, it's under-predicting, right? Because if it was a perfect line like this, these would be up higher. So for higher prices, it's under-predicting. So the model does have a few problems that sort of start showing up here. One other way that we can sort of see how the model is going to do, if we look at the residual sum of squares. So this is the residual sum of squares. It's kind of meaningless on its own, but if we look at the mean squared error, this is the average difference, like the average deviation for our prediction versus the actual price. And actually, so this is what you would look at in order to maybe choose a model, look at how well this model is predicting this one versus another one. So if we want to fit a different model and look at this quantity, we'll talk about that later when we talk about cross-validation, things like that. Okay, so so this is so instead of fitting all of them, what we want to do now is just fit one. Just fit one explanatory variable or one feature or one predictor. These are all, they all mean the same thing. And so we're just going to fit one, and then I'll leave you guys another model to fit for as an exercise. So, so this is, again, we looked at this before, but this one kind of looked the next best sort of ripe for picking in terms of fitting a linear regression through the pupil per teacher ratio. Okay. So I'll leave this one for you to do, because I do want to talk about the things that are sort of the important things to think about. I put it in red because it's like, do think about these. It's like, warning. So the things that the linear regression is assuming is that the dependent variable or the outcome or the target y is a linear combination of the regression coefficients beta and the independent variables x. And so if you don't have this relationship, meaning if you see a curve in your scatter plot, you can't expect this model to fit well. So that's sort of the warning. And we, in real life, we see all kinds of, like this, having just sort of a linear combination is a very, very simple model that will give you information, but it won't necessarily fit well all the time. And so this might be one reason. The other reason is constant standard deviation. So from that figure up top, what constant standard deviation means is that when you look at your scatter plot, if you see that on this end there's a very wide range of values, kind of like in the pupil to teacher linear regression, and here you see much shorter, much narrower bands, that's something else that can go wrong. Okay, so sort of going back to this here, you see that not only is there maybe not so linear of a relationship, but this band is gigantic compared to this band here. And so that's another indication that the linear regression might not be the best. Let's see, what was the other thing? Normal distribution for the errors. So again, looking back at that shape, if you don't see a large clustering near the center for any particular x, then it might not fit well. And the other thing is independent errors. So this one is a bit tougher because a lot of times you're going to have data that is correlated with each other, meaning the actual points are related to each other in some way that you might not understand. And so this is a very strong assumption that you kind of mostly have to make. If for some reason you don't believe that you have independent errors or in any case independent observations, there's many more models that don't assume this, and so you should use one of those. But we won't talk about those now. But just something to think about mostly. Okay, so that's enough about linear regression, although we are going to talk about it next. But first, let's talk about training and test data sets. Training and test data sets is something that you see a lot, especially in the machine learning field. And so the main purpose of training and test data sets is to try to get a feel for how well your model is going to fit to new data. So this goes back to the initial point. The purpose of linear regression that I talked about at the beginning was prediction. So the training and test data sets, the way that it's set up is you have a gigantic data set, you take out a chunk, you fit a linear regression on the rest, and then you see how well your regression will do for the other points that you left out. And the purpose of it is to give you an idea of the predictive ability of the model. Because if you have new data points and they're not predicting very well at all, then you know that your model is not going to be able to predict not only on these, but on any future observations that you might observe. Okay, so so the way that we do this, so here's just an example where I do it by hand, and what I'm going to do is I'm going to leave out. So I'm going to drop the last 50, and I'm going to save those as my test data set. I'm going to keep the rest as my training data set. So there's going to be this many in my training data set, and then 50 in my test data set. And I do the same for the outcomes. And then, so this is one way to do it. So there are some things that can go wrong when I do something like this, right? So if for some reason the data is ordered in a particular way, like let's say more expensive houses are at the top or at the bottom, then my test data set is not going to be reflective of my training data set. So this is generally not a good way to do it. A better way to do it is to do random splitting. So you just randomly leave out. So in this case, I'm leaving out 33%. And so if you've never seen this before, you can just do read up a bit on this function by uncommenting that and running it. So let's get that. And so you see here, so it randomly selected 167 to be my test, and then 339 to be my training data set. Okay, so it says your turn, but I did it for you. So first thing I'm going to do is I'm going to fit on the training data set, and then so this linear models module has a .predict, which I can give the x's to, and it'll predict my y's. And if I give it the training data set, it'll give me a prediction for the training data set that I use to build the model. And if I give it a testing data set, testing x's, it'll predict the y's for the test data set. And so the reason I wanted to do this is because I wanted to show you guys this. So what is this saying? This is saying that if we use x to train the model, it's going to have a lower mean squared error than if we use the training, if we actually predict on the training data set. And this is a phenomenon called overfitting, because we used the data. The way that we used the data was, say, fit the best on this data. So we expect that if we actually use that same data to predict, it's going to fit the best, because that's the requirement that we gave it. Okay, so if we actually plot the residuals, you can see that the training. So you can see that there are some observations here that are quite big, that are contributing to a larger mean squared error. Okay, so the next thing that I want to talk about is just a very simple extension of the train test procedure, where we took a data set, we've split it into two, one for training and one for testing. And this is called a cross-validation. And in this case, I'll just give it the long name k-fold cross-validation, because what you're going to do is you're going to, so it's just a natural extension of the test train split. And the reason why it's important is because if you fit your data on two-thirds if you fit your model on two-thirds of your data, and then you test on one-third, it seems like there might be a way to get a better sense of prediction error by somehow doing this over and over again, and sort of partitioning out your data, fitting on one part, testing on the other, do it again and again. And so that's what k-fold cross-validation is. And the way it works is you have k groups, so let's say 5, and you're going to randomly assign your n samples to those k groups. So you're just going to sort of randomly split them up. So each of them is going to have about n over k samples. And so for each group, you're going to fit the model on all the data except that group. So you're going to hold it here separate. You're going to fit your linear regression or whatever it is here. And then you're going to predict this and look at the prediction error for that group. And then you do that again for all the groups. And by the end, you'll have the average prediction error, which I'll call error cross-validation error. See, so this way you'll have a cross-validation error that has a bigger number, so it'll give you a better idea of what error you might expect in the future for future observations. Okay, so actually, so I won't do this here, but if you just go to this to the scikit-learn documentation, it's very easy, and it's actually it looks just like this, but you do cross-validation here. Okay, so so the next thing I wanted to talk about was either do another linear regression example, which I might actually skip because I think what I want to talk about is so there are different types of regression. So in this tutorial, we talked about linear regression, and we're going to talk about logistic regression in a bit. But there are many types of regression. There are some that have less assumptions, some that have different kinds of assumptions. So if you just go to this link, you'll see this is very nice sort of explanation about when you should use what kind of regression. So there's all kinds of regression, and they all have very nice features. They also obviously all have some drawbacks, but you can use a lot of these, and we'll encounter some of these later on as well. But the next thing I want to talk about is logistic regression. So if you noticed in the previous sections, we had outcomes that were continuous, like the price of the median house in a particular town. But what if you have labels? So like a binary label as an outcome, like cancer patient, not cancer patient, and you have all this data for each of them. Can you predict? Can you use these predictors to still model in the same spirit their outcome? And it turns out you can, and this is probably the second oldest form of regression, the oldest being linear regression. And the way it works is it models the probability of seeing a 1 given this weird looking function, and we'll see sort of how it looks and how you can use it in Python. So the example that I want to give is this. This is a very classic example. So the Challenger shuttle exploded in 1986, and they spent a long time trying to figure out what happened. And so they actually called up a bunch of people to come and try to figure out what happened. And they eventually found out that these O-rings, which are this ring that somehow holds things together here. I'm not sure all the details, but anyway, it turns out that those fail for particular temperatures. So if it's a certain temperature outside, they fail at a higher rate, and so that's actually really important because you can't control the weather, and you have to do your launch no matter what. So it's actually really important to understand the relationship between temperature and whether or not this thing is going to fail, because it was such it was kind of a massive failure. Okay, so here's the data set so this is from tests, and it was actually controversial because the people were aware of this test, but they didn't sort of link it together. So this is a temperature reading and whether or not the ring failed at that temperature reading from testing from the company that built that. I think eventually they didn't actually blame NASA for it, but anyway, they still had to find out what happened. So here's the data. So obviously this is in the era of not big data, but small, tiny data. There's only, I don't even know how many, 20-something, or I don't know, 20-something data points, 20-something temperature readings, and whether or not the O-ring failed at that temperature reading. So not big data at all. And in fact, at this point, they probably didn't do the calculations by hands, but they probably could have. if they wanted. And so I'm actually going to just do this in one go. I should have separated them out, but so here is the fit of the logistic regression, and so the logistic regression coefficients are a bit harder to interpret because if you remember that the x's are related to y in this weird logistic fashion, so it's not as easy to interpret these as it is to interpret linear regression, but you can always interpret the sort of the sign of the coefficients, and you see that that it is significantly different from 0 here. So what this is saying is that it does seem that temperature is related to whether or not the O-ring failed, but not only that, it's negatively related. So so higher temperatures means lower probability to be a 1, meaning lower probability to fail. And so this is actually one of my favorite plots. Can I say that? Yeah, probably. This is one of my favorite plots to look at when I'm looking at logistic, or when I'm looking at logistic modeling is, so here's the actual data. So the blue dots are the actual data, the observations. We see that at temperature 65 point whatever, maybe 66, yeah, probably 66, that there was no failure. But you see that there are many, many more up here, and there's essentially none down here. But this was obviously at this temperature, it failed regardless of the temperature. So there might have been something else wrong, which we're not understanding yet. But yeah, so that's all I wanted to talk about. So I'm a few minutes short, but I think that's probably okay. Yes. Yeah. Do you have a question?
No, I just wanted to ask sigmoid function versus logistic function. Mm-hmm. You have mentioned, like, are they the same thing? Like,
yeah. So the question was whether or not sigmoid functions and the logistic functions were the same. So sigmoid is actually the function for not a logistic regression, but what is it called? A probate regression? Yeah. So it's used for probate regression, and the assumptions are a little bit different. So they're not the same thing, but
they have almost the same look.
But they look very similar. Yeah. So if you see in this, so if I were to fit a probate regression, this wouldn't have such it would have to have a sharper bound because it's based on the normal distribution, and it has like faster decreasing tails. Yeah. Okay. So I did want to go over a bit on the actually how to fit logistic regression using stats models, because I didn't realize that. Of course, up above I used sklearn to fit the linear regression. So this is just so that you can see different ways of doing that, and you can see that I can import not only logit from stats models, but I can also import OLS. So I could have done this with stats models up above instead of using sklearn. But this is just so you can see many different ways to do it. And so the first thing I did was I like working with pandas data frames as well as most of you do by now. And so I made it into a data frame where I renamed the things because the names are kind of not informative. And so here's how you fit a logistic regression. So you do that by modeling. So whatever's on the left is going to be your y, or your outcome variable, and then whatever. Then this is it looks like a minus sign here, but it's actually a tilde. You should be able to see it in your computer. So it's a tilde. That's the shift version of the top left key on most computers. So it's a little wavy tilde. And then on the right-hand side, you're going to put the things that you're going to use to predict the failure. So your x's. And if you have multiple x's, in this example we just had one, but if you have multiple, you can use x1 plus x2 plus x3, whatever you want, and it has to be obviously in the data frame. And so that's how you use. So this is called formula notation, and not only they don't actually this is very similar to the R formula structure, if you're familiar with that. I'm not sure if other languages use it, but it is very common in statistics. Okay, so then the other thing is, if you actually want to give the summary, which I kind of went over very quickly, if you want to give the summary, you just say print, then you put the summary function here. Okay, so then the last thing was, how did I draw that line? And what are all these things? So the way that I did it was I wanted to actually explicitly show you, instead of just having it automatically draw for you, explicitly show you how do you get that fitted line. Meaning, so these probabilities. So the height here of this function is the predicted probability of failure at this temperature. So at temperatures around the range of 50 to 55, it has a very, very high probability of failure. And so how did I get that function? So how I got that function was so we have predicted values. So we have beta hats. So the way that I can get them is I can get, so I put in P the params, so the parameters from the model, and then I actually went and got them. So this is the intercept parameter and the temperature parameter, and I looked at it for varying temperatures. So x is going to be my temperature here.
And the intercept is intrinsic, right? You don't have to specify it in the formula. It
Right.
just gives it for you.
Right. So it automatically gives you an intercept. Oh, yeah. So in the model, if you don't put anything here, it automatically fits the intercept. That's correct. If you don't want an intercept, so we talked about this earlier, the way that you do it is you say 0 plus. So you notice here that there is no intercept. Obviously, there's an error because I try to get it here. But if you don't want the intercept, you say 0 plus then whatever else. And that's a way of you. That's a way for you to tell the logistic regression fit not to fit an intercept. Okay.
And you could fit linear models in the same way.
Yes.
So then you'd replace logit by OLS.
Exactly. Yeah. So yeah. Again, the OLS and these all work in the same way. They all have this formula notation. So we could do the ones up above using this exact structure, but of course putting OLS here instead of logit. Okay. So once I got the parameters, I can plug them into this formula, which I got from here, right? So it's just the sum of the betas and the x's. And of course here, I did forget the beta 0 here. So it should be beta 0 plus the rest. Although if you put a column of 1s for your x1, then it'll fit the intercept. And then what I did was I put whatever x I got here, and I put it through this function. And so that's how I got this probability that y is equal to 1, the height of that function. So I just did it manually so that you could actually see where this function is coming from. And the other thing was the p-values. So in the homework, we're going to ask you to interpret the p-values. So there's a very formulaic way to interpret the p-value, but the way that I want to talk about it is actually, okay, so what does the p-value mean? So the p-value is testing the hypothesis that this coefficient is 0. And having a low probability, meaning a very, very small probability, so that's the probability that your observation that this coefficient is this value just happened purely by chance. All right, so having very small values of the p-value means that this relationship is not by chance. So there is something there, and in the homework we're going to talk a bit about multiple hypothesis testing, because you see that the intercept is also significant by our standards of comparing it to 0.05. But we have two hypotheses. So what do we do? How do we deal with that? So that's something that there's going to be a fair amount of reading in the homework about it, but also we can talk more about it in future sections as well if there's any concerns. But okay, I think that's everything for today. Enjoy your next homework or finish the current homework. Good luck with that.